आवाज आ रही है ना? कोई बोल नहीं रहा। हेलो।
आवाज आ रही है अफरोज साहब?
जी जी।
1 मिनट। सर ये यूट्यूब पे लाइव स्ट्रीम स्टार्ट हो गया है।
ठीक है सर।
हेलो। हेलो सर, आवाज आ रही है?
जी आ रही है, आपकी आवाज आ
जी
रही
जी।
ओके सर, ओके, थैंक यू।
व्हाट्सअप आवाज आ रही है सुभाष सर?
हाँ आवाज आ रही है, बिल्कुल आ रही है आवाज।
ठीक।
Good morning to all of you.
गुड मॉर्निंग सर। गुड
गुड मॉर्निंग सर।
How are you?
फाइन सर।
Right.
No videos on there. You see that?
हेडफोन लगा दो सर।
आवाज आती है ना?
Hello, am I audible? सुभाष सर, आवाज आ रही? Assalamu alaikum. A very good morning to one and all. On behalf of Department of Mathematics, School of Sciences, Maulana Azad National Urdu University, Hyderabad, it's my pleasure to welcome you all to this today's online International Symposium on Differential Geometry and its Application 2022. Before we get started, I would like to invite Mr. Fazle Rasool for recitation of Holy Quran. Mr. Fazle Rasool?
Yes, sir.
Yeah. Over to you.
Assalamu alaikum wa rahmatullahi wa barakatuh. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. اقرأ باسم ربك الذي خلق. خلق الإنسان من علق. اقرأ وربك الأكرم الذي علم بالقلم. علم الإنسان ما لم يعلم. كلا إن الإنسان ليطغى أن رآه استغنى. إن إلى ربك الرجعى. أرأيت الذي ينهى عبدا إذا صلى. بأن الله يرى كلا لئن لم ينته لنفسعا بالناصية ناصية كاذبة خاطئة فليدع ناديه سندع الزبانية كلا لا تطعه واسجد واقترب صدق الله العظيम। तर्जुमा। शुरू अल्लाह का नाम लेकर जो बड़ा मेहरबान निहायत रहम वाला है। आए नबी सल्लल्लाहु अलैहि वसल्लम अपने परवरदिगार का नाम लेकर पढ़ो जिसने तमाम कायनात को पैदा किया, जिसने इंसान को खून की फुटकी से बनाया। पढ़ो और तुम्हारा परवरदिगार बड़ा करीम है, जिसने कलम के जरिए इसे इल्म सिखाया और इंसान को वो बातें सिखाई जिनका उसको इल्म न था, मगर इंसान सरकश हो जाता है इस बिना पर कि वो अपने आप को बेनियाज समझता है। कुछ शक नहीं कि सबको तुम्हारे परवरदिगार ही की तरफ लौट के जाना है। क्या तुमने उस शख्स को देखा जो मना करता है एक बंदे को जब वो नमाज पढ़ने लगता है? भला देखो तो अगर या राह रास्त पर हो या परहेजगारी का हुक्म करे तो उसका अंजाम क्या होगा? जरा देखो तो अगर उसने दीन हक को झुटलाया और उससे मुंह मोड़ा, क्या उसको मालूम नहीं कि अल्लाह देख रहा है? देखो अगर वह बाज ना आएगा तो हम उसकी पेशानी के बाल पकड़कर घसीटेंगे, यानी उस झूठे खताकार की पेशानी के बाल। तो वह अपने याराने मजलिस को बुला ले, हम भी दोज़ख के फरिश्तों को बुलाएंगे। देख उसका कहा ना मानना और सजदा करना और अल्लाह का कुर्ब हासिल करते रहना। Translation. In the name of Allah, the entirely merciful, the especially merciful. Recite in the name of your Lord who created man from the clinging substance. Recite, and your Lord is the most generous, who taught by the pen, taught man that which he knew not. No, but indeed man transgresses, because he sees himself self-sufficient. Indeed, to your Lord is the return. Have you seen the one who forbids a servant when he prays? Have you seen if he is upon guidance or ingenious generousness? Have you seen if he denies and turns away? Does he not know that Allah sees? No, if he does not desist, we will surely drag him by the forelock, a lying, sinning forelock. Then let him call his associate. We will call the angel of hell. No, do not obey him, but prostrate and draw near to Allah. Thank you.
Thank you, Mr. Fazli Rasool. Once again, I welcome all of you to this today's online international symposium on differential geometry and its applications 2022. I'm also pleased to welcome all the eminent speakers and guests from different countries and from different institutions. Of course, you have joined us to share your knowledge and vast experience with the young students and researchers working in the field of differential geometry. Eric Bell, a Scottish mathematician, once said that mathematics is the queen and the servant of sciences. I think this is a great way to think of the power and scope of mathematical thinking. Differential geometry provides us a tool to visualize abstract things geometrically. During the next 2 days, we will be learning about different investigations and developments in the field of differential geometry. Our talks are planned to be delivered by renowned geometers from different countries such as Romania, Saudi Arabia, Algeria, Turkey, India, Iran, among others. During this symposium, some of the topics to be covered include, and of course not limited to, some manifold theory, fiber bundle, harmonic morphism, homogeneous symmetric spaces, structure on manifolds, theory of relativity, and allied areas. There will be in total 13 invited research talks and a few contributed talks. I hope these 2 days will help all of us to learn theory of differential geometry in a better way. So once again, a very warm welcome to each and everyone who is present over here.
Hello.
Thank you.
Assalamualaikum, sir.
Thank you very much for listening. And now I request Dr. Subhash Allah to play Manu Tarana. Subhash Allah, sir, over to you.
Okay, sir.
मैक्सिमम कल मीटिंग में थे और पूरे लोगों से बैच दी गई कि पूरे आज सबमिट करो और इंशाल्लाह मैक्सिमम हो जाएगा।
ये जामियाए ज़बान उर्दू, ये जामियाए ज़बान उर्दू, ज़बान उर्दू का आशिया है, ज़बान उर्दू का आशिया है। ये जामियाए ज़बान उर्दू, ये जामियाए ज़बान उर्दू। कलाम सारे है दर्ज रूह में,
अपना YouTube जो है ना वो खोल के देख लो चल रहा है कैसे।
कलम से उतरा हुआ बदन है, ये इल्म का शहर घर है मेरा, मेरा मदरसा मेरा वतन है। तालीम का मौसम है, तहजीब की फसलें हैं, हम रोशनी करते हैं, सूरज की नस्लें हैं। उर्दू की उड़े खुशबू, ये जामियाए ज़बान उर्दू, ये जामियाए ज़बान उर्दू, ये जामियाए ज़बान उर्दू, ये जामियाए ज़बान उर्दू। जो दाना गुजरे थे इस ज़मीन से, जो दाना गुजरे थे इस ज़मीन से, वो इल्म के बीज बो गए हैं। बड़े हुए जब पौधे बढ़ के, हमारे कद ऊंचे हो गए हैं। हम चांद की पेशानी जब छू के निकलते हैं, तुम्हें पाओ और सब चलते हैं। उर्दू की उड़े खुशबू, ये जामियाए ज़बान उर्दू, 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 ज़बान उर्दू का आशिया है, ये जामियाए ज़बान उर्दू।
पूरी लिस्ट आपके सामने रखी गई थी। जी जी, नहीं मैं एग्री करता हूँ सर।
Okay, thank you very much, Dr. Subhash Allah.
रिक्वायरमेंट भी आपके सामने।
Now I request Dr. Afroz, head of the Department of Mathematics, Maulana Azad National University, to address the audience.
कल ये डिसीजन हुआ
Dr. Afroz, over to you.
और आज भी बोलो।
Thank you, Dr. Majid. Am I audible? Am I audible, Dr. Majid?
Yes, sir. Yes, sir.
Good morning to all of you. It gives me immense pleasure to start this auspicious occasion by a heartfelt welcome to everybody. First of all, I express my warm regards to Honorable Pro Vice Chancellor Professor S.M. Rahmatullah for his valuable presence. I also express my sincere thanks to speakers from abroad and our country. I heartily welcome to our Dean School of Sciences, Professor Salman Ahmed Khan, and faculty members of the school. Today, we have gathered here for this international symposium on differential geometry and its applications 2022. The objective of this symposium is to bring together senior and young researchers working in the area of differential geometry to exchange new ideas and to discuss current challenging issues in differential geometry. A big thank to everyone who is present here for joining this symposium. I appreciate to each and everyone who put equal effort to make it big and successful. It is overwhelming that we now count 11 years from the inception of Department of Mathematics, and in that span of time, department progressing geometrically. Presently, department is running MSc Mathematics and PhD Mathematics, and also taking part to teach BSc General courses. The faculty members of the department have diverse research interests like wavelet and its applications, algebra, analysis, fluid mechanics, celestial mechanics, dynamical astronomy, differential geometry, and fractional calculus. Students in the department come from different parts of the country, which makes the teaching and learning environment very rich. The number of students are increasing every year. Hope the series of endeavor will continue in forthcoming days. With these words, once again, thanks to all of you for your presence. Thank you very much. Now, go to Majid.
Thank you very much, sir, for your kind words. Now, I would like to invite Dean of the School of Sciences, Professor Salman Ahmed Khan, to address.
Thank you, Dr. Majid Saab. Am I audible?
Yes,
Dr. Majid?
Yes, sir. Yes, sir.
Good morning to everyone, and a very warm welcome to all of you to this international symposium on differential geometry and its application. I'm extremely happy to welcome our Honorable Pro Vice Chancellor of Maulana Azad National Urdu University, Professor S.M. Rahmatullah sir, and a speaker from very prestigious universities. Furthermore, on the behalf of School of Science, Maulana Azad National Urdu University, it is my pleasure to welcome all the delegates of this symposium who joined online. Your presence in this symposium is highly enthusiastic for our organizer and highly appreciable. Maulana Azad National Urdu University was established in 1998. Presently, Maulana Azad National Urdu University has 7 schools and 19 departments. We have more than 10 campuses all over India, like Srinagar, Lucknow, Bhopal, Sambhal, Aurangabad, Bihar, Cuttack. School of Science was established in 2006. School of Science has 1 department of mathematics and 4 sections, including physics, chemistry, zoology, and botany. Currently, we are running undergraduate courses in life sciences and physical sciences and postgraduate program in mathematics. In addition, all the sections and departments are actively involved in research and PhD program. I congratulate the Department of Mathematics, School of Science for organizing this symposium, which focus on current challenging issues in differential geometry. The differential geometry is a mathematical discipline that studies the geometry in different manifold and their submanifold. Differential geometry deals with application method of local and global analysis to geometric problem. Differential geometry has application in mathematics and many other scientific disciplines, for example, medical imaging, computer vision, geometric thermodynamics, geometric design, geometric control, and information geometry. Therefore, I hope this symposium is benefit the researchers of the mathematics and other disciplines, including chemistry, physics, material science, and health sciences. Again, I appreciate the effort of the mathematics department and expect this symposium will be great success. Thank you all. So over to you, Dr. Mazin.
Thank you very much, sir, for your kind words and encouragement to the Department of Mathematics. And we hope that we will fulfill your desired, as you expressed. So now I would like to invite our Honorable Vice Chancellor, Professor Rahmatullah Saab, to address the audience and say something. Sir.
Right. Thank you. Thank you very much. I think I am audible.
Yes, sir. Yes, sir. You are, sir.
Right. A very good morning to all of you. First of all, let me convey my congratulations to the Department of Mathematics and School of Sciences, for coming forward to conduct international symposium on differential geometry. I have gone through the list of participants and I have seen that a number of participants are there from different countries of the world. And really, it's a great thing. It's a great thing to feel pleasure as well as proud also, because the School of Sciences in Manu is conducting such a wonderful program. In the School of Sciences, senior person like Professor Sayyid Najmul Hasan Sahab is there, and the Dean of the school, Professor Salman Ahmad Khan, is also there, and other guest faculties and regular faculties are also there. And they are working like anything, and they are trying their level best to take the department to the highest level. And for that, I think they deserve to be congratulated, as well as they deserve to be thanked. Well, coming to the point, let me say that you may say it geometry or differential geometry, and it's a part of mathematics. But for me, a person who is not from the field of mathematics, geometry means not mathematics, but it's a compulsory requirement of human life. It's a requirement to facilitate the human life. If geometry is there, more and more facilities will come in human life. Otherwise, the human life will be deprived with more and more facilities. So in that context, I presume that this symposium has assumed considerable significance and importance. I hope and believe that during the days of this symposium, fruitful talks will take place, and the symposium will come forward with quality output, so that the differential geometry can be enriched, and in other words, the human life will be more facilitated. So with this word, I conclude with once again expressing my heartfelt thanks to all the organizers, more particularly to the faculty members of the department, as well as the senior faculty of the department, Professor Sayyid Najmul Hasan Sahab, and the Dean of the school, Professor Salman Ahmad Khan Sahab. All the best, and Jai Hind.
Thank you very much, sir, for your encouraging words. Thank you again. This international symposium will be consisting of actually 13 invited lectures. And we will be starting with our first lecture at 10:30 sharp. And that lecture will be delivered by Professor Absus Ali Sheikh. And in the morning session that is going to be started from 10:30 onwards, we will have 4 lectures. The first lecture is, as I told, Professor Afsoos Sheikh. The second will be from Professor Mohammad Bel Khalfa. The third will be from Professor Jafar Hassan. And the fourth will be from Professor Sirajuddin, Saudi Arabia. And in the session B, that is to be started after lunch, because we have given a break of lunch from 1:10 to 2 p.m. So we will have our fifth and sixth invited lectures. First will be from Dr. Sudhakar Kumar Chobe from Oman. Second will be Dr. Mehmet Akif Akyol from Turkey. And the session sheet that is expected to start from 3:30 will be consisting of short lectures, I mean contributory lectures. And it will be of 6 lectures together, delivered to be by Dr. Danish Siddiqui from Saudi Arabia, Dr. Mubin from Integral University, Dr. Ram Shankar Gupta from Indraprastha University, Delhi, Dr. Alia Nas Siddiqui from Punjab, Dr. Kamran Khan from Aligarh Muslim University, Dr. Sushil Shukla, and Dr. Inan Onal from Turkey. The second day, that is tomorrow, again we will have the same schedule, and we will be starting from 10 a.m. sharp. The first lecture will be from Professor P.K. Sahu from BITS Plani, Hyderabad. And second lecture we will have from Professor Belji Ali from Algeria. And third lecture from Professor Sudhir Kumar Srivastava, Head Department Mathematics, Gorakhpur University. The fourth lecture will be Dr. Najrul Islam Khan, Qasim University, Saudi Arabia. And we have our fifth invited lecture from Professor Vishnu Nara Mishra. The sixth lecture that is expected to be started after lunch from 1:10. The first lecture will be from Dr. Rakesh Kumar from Patiala University, Punjab. And the second lecture will be from Professor Habil Adela Gabriela Mihai from Romania. And similarly, we will have a contributory talk section that is from 3:30 onwards. Will be consisting of 6 lectures to be delivered by immigrant geometers, young geometers from different countries, such as Professor Fasihi Ramadi from Iran, Dr. Agajin Bahadur from Turkey, Dr. Sabina from West Bengal, Dr. Muhammad Akif from Delhi University, Dr. Anu Degan from Punjab, and Dr. Abdul Malik Muhammad from Algeria. So I have summarized the whole schedule before you guys. So now I may request Dr. Khwaja Moinuddin sir. Are you there, sir?
Yes, yes.
Yeah. May I request you, sir, to please say a vote of thanks.
Thank you.
Over to you, sir.
Majid Ali. Thank you, Majid sir. Assalamu alaikum wa rahmatullah. A very good morning to one and all. It gives me immense pleasure to deliver the vote of thanks for this event to all the dignitaries, participants, and the associated faculty and students. I would like to thank our chief guest, Professor S.M. Rahmatullah, Pro Vice Chancellor of Manu, for gracing this occasion and presenting his inspirational thoughts. Thank you, sir. I would like to thank our Dean School of Sciences, Professor Salman Ahmad Khan, Professor S.N. Hassan, sir, Dr. Afroz, Head Department of Mathematics, and all my colleagues. I would like to thank all the distinguished professors delivering invited talks who have been joined from different countries. And I would like to thank Professor Zafar Hassan, sir, also. He has joined, I think. I would like to thank all the participants who are present in this session and who are supposed to join. Lastly, but not the least, I thank all the research scholars of the Department of Mathematics for their support and all others associated persons. Once again, I thank one and all. Thank you, sir.
Thank you very much, sir. Before we conclude this inaugural session, and I'll request Dr. Subhash Ala to play national anthem.
Associated persons.
Actually, we all of you have chosen to be part of this international symposium because all of us have a mutual passion for differential geometry. And this passion help us all to unite, and the energy we create is what allows us to achieve our individual as well as collaborative research goals in the field of differential geometry and its applications. So I request all the participants to listen the lectures to be delivered by eminent geometers carefully and to be interactive. I request all the participants to be interactive. One more thing is there. All the eminent speakers are joining us with the help of Zoom link, and all the attendees are actually they are watching us live on our YouTube channel. So with this, I conclude here, and now I request Dr. Subhash Alla to play national anthem, and may I request everybody to please stand up at their respective positions so that Indian national anthem is played by Dr. Subhash Alla. Thank you.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, Dr. Subhash Alla, and thank you, everyone. Our first lecture of the session will start at 10:30, and our first speaker will be Professor Afsoos Ali Sheikh from West Bengal, Burdwan University. Sir, are you there, sir?
Yes.
Assalamu alaikum, sir.
Good morning, Dr. Majid.
Good morning, sir. Sir, your voice is breaking, sir. You are not audible properly, sir.
Am I audible clearly?
Yes, sir. Now you are audible, sir.
Okay.
Maybe during the sessions, except for the speaker, others can switch off their videos just to save the bandwidth.
Yes, sir.
Right?
You
So
are
only
right.
when they are speaking, we can switch on if required. The speaker can keep it on, but maybe we'll switch off to make it faster.
Yes, sir. You are right, sir. Hello, sir. Afsoos Ali, sir, Afsoos Ali, Professor Afsoos Ali Sheikh, sir. I think you can check your PPTs or your lecture.
Yes. Yes, Dr. Majid. Can
Sir.
I share screen?
Yeah. You can. Please.
Yeah. But it is shown that host is disabled participant screen sharing.
Please, sir. Share your screen, sir.
Okay. Is it visible?
Yes, sir. It is visible, sir. It is visible, sir. Sir, we will start at 10:30.
Okay.
Geometry of release. सर कभी देखिए शॉर्ट टर्न पे ही है
इसका
जफर सकते हैं।
अगर नहीं
हाँ सर
आपके बिकी शॉर्ट टर्म
उसमें अब्स्ट्रैक्ट देखिए सर का उसमें दिया है
दिखाइए कहाँ
ये मेल कर रहा हूँ कल ही तो मेल किया था उसने मैंने व्हाट्सएप किया था आपको
किया व्हाट्सएप
हाँ abstract ये है सर्कल की सॉल्टॉन एंड स्पेस टाइम ऑफ जनरल रिलेटिविटी।
अरे नहीं
हाँ सर ये देखिए ये इनवाइटेड टॉक 3
सही है
आयशा मुझे तो हेडफोन चाहिए
सही
हेडफोन रश्मि के देखिए पर्स में पड़े हैं कोई हेडफोन
अरे वाह बहुत बड़ा
अब ये इस पे बहुत काम कर रहे हैं सर ये पी को सब हो गया पूरी टीम
किस पे
एफआर ग्रेविटी एफआरटी ग्रेविटी ये इस पे पी के सब हो यूसी डे
अच्छा ये पहले दिन के टॉप से
हाँ इसमें तो सब होगा आपका भी होगा सर लास्ट में देखिए हाँ
सबसे आखिर मेरा ये
लास्ट में ही
मेरा ख्याल सबसे आखिर में तो उन रेफरेंस भी भेजे
हाँ देखिए ये वो डॉक्टर
अनुदेव
ये आपको डॉक्टर Hello. So it's 10:27 now, and this session will be chaired by Professor Syed Najamul Hassan. The next session will be chaired by Professor Jafar Ahsan Khan after lunch. So now I hand over to Professor Syed Najmul Hassan. Sir, are you there, sir?
Yeah.
Okay, sir.
Thank you, Dr. Majid. We are slightly ahead of time, but maybe we can use that to introduce the speakers. So I welcome you all for the first session of the online international symposium on differential geometry and its applications. In this session, we have 4 speakers of great eminence. And the speakers we have are Professor Afsoz Ali Sheikh, Professor Muhammad Bil Khalfa, Professor Zafar Ahsan, and Professor Sirajuddin. I'll introduce each speaker just a little before his talk, and a few directions to the people who are online and attending the conference. If there are any questions, please put them in chat. If you are in the Zoom session, you can put it in the Zoom chat. If you're on the YouTube, you can put it in the YouTube chat. And at the end of the talk, we'll request this respective speakers to address to those questions. So the first talk is by Professor Afsoz Ali Sheikh. He'll be speaking on geometry of Ricci solitons. Professor Afsoz Ali Sheikh is from Department of Mathematics, University of Burdan, which is in West Bengal, India. He has obtained his PhD from University of Kalyani. He is the recipient of National Scholarship, Certificate of Merit, Satish and Tulsi Mannan Memorial Endowment Bronze Medal for securing highest marks in the Faculty of Science of MSc examination. University Research Fellowship, S.N. Bose Birth Centenary Young Scientist Award 1999. He was a UGC Visiting Fellow of Karnataka University and Sardar Patel University. Professor Afsoz Ali Sheikh has a vast experience, over 25 years of teaching experience and a very rich administrative experience. He has been the head of the Department of Science and Humanities, the member of governing body of teachers in charge of Raiganj Polytechnic, Government of Bengal. He has acted as the head of Department of Mathematics. He's been the controller of examinations, member of the University Court Council, coordinator of NET/SLET Coaching Center of UGC. He has about 18 PhDs awarded to his under his supervision, and 8 more are working with him. He has visited Chu University, Tokyo Science University, Kunpul National University, Gyeongsang National University, Ulsa University, South Korea, Debrecen University, Hungary, and he has also given talks in various places in India and Bangladesh. So I would not come between the speaker and you much longer, and I request Professor Afsoz Ali Sheikh to deliver his talk. Yes, sir. Geometry of Ricci solitons.
So, okay, thank you, Professor Hassan. for the nice introduction. First of all, I would like to convey my sincere thanks and gratitude to the organizer of the International Conference of Differential Geometry and its applications, especially Dr. Majid Choudhury, for the invitation. The title of my talk is Geometry of Rishi. In 1904, all of you, well known to all of you, Henry Poincaré proposed a conjecture that are known as Poincaré conjecture, which states that existence of a closed three manifold is homeomorphic with three sphere. Then in 1982, Hamilton introduced the concept of Ricci flow to counter the famous Poincaré conjecture. Finally, in 2006, Perelman solved the conjecture. He was submitted his papers in Archive Math in 2002, 2003. Now, what is Ricci flow? The Ricci flow is defined by an evolution equation for matrix on the Riemann manifold AMG0, where G0 is the value of the metric tensor G at the time t equals to 0, initial conditions. Satisfying this differential equation 1, and Rig GT is the Ricci curvature of the metric GT for some t greater than 0. A solution of the form GT equals to 1 minus twice lambda t phi t upper star G0, where lambda is a real constant and phi t is one parameter group of diffeomorphisms of a vector field X, is known as the self-similar solution of the Ricci flow. Phi t upper star is the pullback of phi t. Next, a complete Riemannian manifold Mg of dimension n greater than equals to 2 with Riemannian metric G is said to be a Ricci soliton if there exists a smooth vector field X satisfying the equation 2, where lambda is a real constant and Lxg is the Lie derivative of the metric G in the direction of the vector field X. The Ricci soliton is said to be shrinking, steady, and expanding according as lambda greater than 0, equals to 0, or less than 0 respectively. If the vector field X is gradient of some smooth function f, then the Ricci soliton is said to be gradient Ricci soliton. And in this case, the previous equation 2 takes the form equation 3, where del 2f is the Hessian of the function f. And this function f is known as the potential function of the Ricci soliton. Perelman proved that a Ricci soliton in a compact Riemannian manifold must be gradient. In dimension 2, Hamilton, the reference is here, completely classified shrinking gradient Ricci solitons with bounded curvature and proved that they are the two spheres, the projective space and the Euclidean space with constant curvature. In case of dimension 3, Perelman proved the following. Let MGF be a three-dimensional non-flat gradient shrinking soliton with bounded non-negative sectional curvature and K non-collapsed on all scales for some positive K, then MGF is one of the following: the round three-sphere S3 or its metric quotients, the round infinite cylinder or its Z2 quotients. The Perelman's result has been improved by Tao, Chen, and Zhu in 2008. This paper published in Survey Differential Geometry, where they removed all curvature bound assumptions and proved that if MGF is a three-dimensional complete non-flat shrinking gradient soliton, then it is a quotient of the round sphere S3 or round cylinder S2 product term. Later, many mathematicians such as Neber, Wang proved the classification theorem for higher dimensional Ricci-Soliton. Each type of Ricci-Solitons determines some unique topology on the manifold. For example, Fang et al. In 2008 showed that if the scalar curvature of a complete gradient shrinking Ricci-Soliton is bounded, then the manifold has finite topological type. In 2017, Montanu and Wang proved that an n-dimensional gradient shrinking Ricci-Soliton with non-negative sectional curvature and positive Ricci curvature must be compact. Again, in 2008, by using universal cover, Fernandez Lopez, Garrica Rio proved that the fundamental group is finite for the compact shrinking Ricci-Soliton. And the same result also proved by Zhang by alternative method. The same result has also been proved earlier by Lott for gradient Ricci-Soliton. Again, Neber generalized this result and proved for bounded Ricci curvature. Next, Wiley, the paper published in Proceedings to American Mathematical Society in 2007, proved the strongest result that any complete shrinking Ricci-Soliton has finite fundamental group. Locally conformally flat Ricci-Soliton have been investigated immensely in the last few years. Tao et al., Peterson and Wiley, and also Zhang classified locally conformally flat gradient Ricci-Solitons, and they showed that it is isometric to Sn, Rn, R1 product, n-1 dimensional sphere, Sn-1, or one of their quotients. Next, convex function. A smooth real valued function phi on a manifold M is said to be convex if for any point P of the manifold and any tangent vector V at the point P, the inner product between grad phi and V at the point P is less or equals to phi of exponential at the point P of the vector V minus phi phi. That means the relation 4 holds. If phi is convex, then minus phi is concave. If the equality in 4 holds, then phi is called an affine function. The behavior of a convex function and the geometry of a Riemannian manifold is inextricably linked. Even the continuity of a convex function largely depends on the volume of a Riemannian manifold. For example, in 1969, Bishop and O'Neill showed that a smooth convex function in a finite volume Riemannian manifold is always constant. St. Yao proved that a continuous convex function in a Riemannian manifold having finite volume is constant. Greene and Shiohama proved that if a convex function in a Riemannian manifold does not admit its minimum, then the manifold splits a line. We have studied the behavior of a convex function in a Ricci-Sullivan, and then we proved the following result. This result is published in the Proceedings of Indian National Academy of Science, Mathematical Sciences, volume 130, year 2020. The theorem states that let MGF be a complete gradient Ricci-Sullivan with non-negative Ricci curvature. If f is a smooth function and is a non-constant convex function with finite weighted Dirichlet integral, that means it satisfies both 5 and 6. Here BPR is an open ball with center P and radius R. Then the manifold M would be the Ricci flat manifold. Moreover, the gradient of f is killing with its absolute value as constant. As a corollary of our result, we obtain that let MGF be a complete non-compact gradient Ricci-Sullivan with non-negative Ricci curvature. If f is a smooth harmonic function with finite weighted Dirichlet integral, then M is a Ricci flat manifold. In 1982, Inami proved the splitting theorem of a Riemannian manifold admitting a non-constant affine function. In particular, he showed the following result. If M is a complete Riemannian manifold without boundary and it admits a non-constant affine function, then the manifold is isometric to the Riemannian product N cross R, where N is a totally geodesic submanifold. By extending the result of Inami, we prove the following result, which is published in the same paper, Proceedings Indian Academy of Sciences. Let M be a complete Riemannian manifold with non-negative Ricci curvature, which admits a non-constant convex function with finite weighted Dirichlet integral conditions 5 and 6. Then M is isometric to the Riemannian product N cross the real line R, where N is a totally geodesic submanifold of M. The existence of a non-constant concave function in a Riemannian manifold has some impact on the type of the Ricci-Sullivan. The following result is a glimpse of the whole picture. This result is also published in the same journal. This is our result. Let the MG be a complete gradient Ricci-Sullivan satisfying the gradient Ricci-Sullivan equation free if f is a non-constant smooth concave function and M has bounded Ricci curvature, that means mod Ric less or equals to K for some positive constant K, then the Ricci-Sullivan is non-shrinking. Now, the definition of critical point of a manifold at a point P of the scalar curvature R on the Riemann manifold M is defined in such a way that its grad of the scalar curvature vanishes at that point. Wu studied the critical point of the scalar curvature in a Ricci-Sullivan and proved the following. Let Mg be a steady gradient Ricci-Sullivan with positive Ricci curvature. Then there is at most one critical point of the scalar curvature. This result was published in Journal of Mathematical Analysis and Applications. We have obtained the following result of the critical point for scalar curvature. This is our result, theorem 12. Let Mg be a complete non-compact gradient Ricci-Sullivan satisfying this equation with lambda non-negative. If f is a non-constant smooth convex function and Ricci curvature of the manifold is bounded 0 less than Ric less or equals to k for some k greater than 0, then there is at most one critical point of the scalar curvature R. We have studied conformally flat Ricci-Sullivan and obtained the following result. This result is published in Journal of Geometry and Physics, volume 140 in 2019. Let MGF be an n-dimensional, complete, non-flat gradient shrinking Ricci-Sullivan satisfying the conditions. The potential function f is non-zero everywhere and its reciprocal is subharmonic. The scalar curvature R satisfies this, belongs to L1M, where L1M is given here. The name is compact Einstein manifold. Curvature. And scalar curvature is given by R equals to 2. Furthermore, if M is conformally flat, then it is formed, and also the manifold is isometric to the n-dimensional Euclidean sphere Sn, provided n is conformally flat. Since you know a three-dimensional manifold, the biconformal curvature tensor C always vanishes. So for three-dimensional case, we can state result. The three-dimensional gradient shrinking Ricci-Sullivan curvature R belongs to L1M and Laplacian is non-negative, is simply connected. Next, the Riemannian manifold M is said to have linear volume growth. If remains minimum volume of this open ball BPR by R finite. For every C belongs to N. Various properties of Riemannian manifold with linear volume growth have been studied by many authors. For example, Ramani, linear volume growth condition, when the curvature restricted condition of the previous theorem, that is a conformally flat, can be omitted. We prove the following. Suppose MGF is an n-dimensional, complete, conformally flat gradient shrinking Ricci-Sullivan with linear volume growth. If 1 by f is subharmonic, then M is isometric to the Euclidean sphere Sn. There is a classification of compact half conformally flat two-dimensional manifold with positive scalar curvature. This is the result given in the book of LBZ. Let M be a compact half conformally flat four-dimensional Einstein manifold with positive scalar curvature. The name is an isometric to CP2. We have also partially classified
क्या हुआ
complete
वहां लगेगा 1.5 घंटा हाँ
Suppose MGF is a four-dimensional complete gradient shrinking Ritchie-Sullivan with 1 by F is subharmonic. If M is half conformally flat and any one of the following conditions hold, either 1 or 2, then M is isometric to S4 or CP2. Therefore, M has trivial fundamental group. This is our result. Next, recently Zhang classified compact four-dimensional Einstein manifold satisfying some curvature conditions and proved this following result. Suppose MG is a compact four-dimensional Einstein manifold with sectional curvature is bounded by this quantity 1 by 12 plus root 30 by 8. Then the MG is isometric to either S4 or RP4 or CP2. Extending the result of Zhang, in case of Ritchie-Sullivan, we prove the following result. Let MGF be a four-dimensional complete gradient shrinking Ritchie-Sullivan with linear volume growth and sectional curvature is bounded by the same quantity. If 1 by F is subharmonic, then MG is isometric to either S4 or RP4 or CP2. Finally, we have showed the following compactness criteria. If an n-dimensional gradient shrinking Ritchie-Sullivan MGF realizes the following conditions: volume of this ball is bounded by CR square for all P belongs to M, R is greater than 0, C is the positive constant, and F satisfies this inequality, then M is compact. In 1968, John Milnor conjectured that the fundamental group of any complete Riemannian manifold with a non-negative Ricci curvature is finitely generated. So these are some pictures of finitely generated manifolds. The conjecture is still open except for dimension 3. In 2080, Japan completely solved the Milnor conjecture for three-dimensional case. The equation of gradient Ritchie-Sullivan is given by Rick plus del 2f equals to lambda g. This is well-known equation. And the left-hand side of this equation is known as Bakry-Emery-Ritchie tensor, or infinity Bakry-Emery-Ritchie tensor. This is denoted by Rick F. So Rick F equals to lambda g. The gradient Ritchie-Sullivan can be written Rick F equals to lambda g. In general, the M Bakry-Emery-Ritchie tensor is defined by Rick F M. This is a notation. This equals to Rick F minus 1 by M differential of F with the tensor product differential of F for M greater than 0. The Ritchie-Sullivan version of Milnor conjecture is the following. The fundamental group of any non-expanding Ritchie-Sullivan is finitely generated. In 2008, M. Fernandez Lopez and E. Garpario proved that if a shrinking Ritchie-Sullivan is compact, then its fundamental group is finite. In 2007, Wiley further modified this result and proved that fundamental group of a shrinking Ritchie-Sullivan is always finite. In 2015, M. Jaramillo proved the following theorem in a Riemannian manifold with a measure this. And the theorem states that let mg e to the power minus f differential of volume G be a smooth metric measure space with non-negative Bakry-Emery-Ricci curvature. Satisfying this condition, mod f less or equals to k and dimension of the manifold less or equals to d for some constant k and d positive, then pi 1m is finitely generated. Fundamental group is finitely generated. Literature shows that the Milnor's conjecture of Ricci-Sullivan has been solved partially. Milnor's conjecture is unproven in case of steady Ricci-Sullivan having infinite volume. Therefore, it is a matter of interest to investigate the following problem, which is open to the audience. When does the fundamental group of a steady Ricci-Sullivan having infinite volume become finitely generated? So with this, I conclude my lecture. These are the references. Complete references here.
Thank you, Professor Sheikh.
My paper is based on my paper 33, reference 33, and another paper, published paper, this is 44. With the best of these two papers, my lecture is, I conclude my lecture. So if there is any question or queries, please let me know. Thank you.
Yeah, thank you, Professor Sheikh. Thank you for the excellent lecture. You've discussed a very important problem from differential geometry and the solutions, how the solutions were achieved, the Poincare conjecture, which was one of the millennium problems, which was solved by parallel movement, but he refused to take the $1 million. So the questions, I see there's one question in the YouTube chat by Dr. S. Srinivas Rao. He asked linear volume growth with respect to what variable? Professor Absos, Sheikh, can you hear me?
Yeah, you see the slide. Is it visible? The slide
No,
is
no, we can't see this, not yet. You'll have to. Yes, we can see now.
Yeah. So this is the slide you see for the linear volume growth. You see this variable.
We can't hear you, Professor.
Yeah.
Yeah, we can see your slide, but we are unable to hear you.
Hello.
Yes. Yes, Professor Sheikh, we can't hear you. We can see your slide on the linear volume growth, but we are unable to hear you.
Yeah. Huh. Am I audible?
Yes, yes. Now you are.
Yeah, linear volume growth. Here you see, this is the condition. Here you see this R approaches to infinity. So this is the variable here. Basically BPR, this is the open ball with center at P and this radius R. So the details is given in the paper. Can I share this paper?
Yes, you can.
Yeah. Okay.
Maybe you can share it in the chat. You can attach the file in the chat group. You are muted, Professor Sheikh. Can you please unmute?
Thank you, sir. May I ask one question?
Yeah, sure. Sure.
Sir, Afsos, sir. Afsos, sir, are you there, sir?
Yes,
Am I
he's
audible?
there. Yeah, we can hear you.
Okay,
Dr.
okay.
Abid Moise, yes.
Is it visible? This slide paper is visible?
Yes, sir. Yes, sir.
Yes.
Sir, in like theorem 13, sir, in theorem 13, please, sir, theorem 13, sir.
Okay.
Sir, your slides are not changing. Yeah, sir. Theorem 13. Sir, there are these two conditions. So these conditions are necessary and sufficient. It means if I remove any of the two conditions, will there be impact on the statement, sir? If, for example, if F is not subharmonic, then what will happen, sir?
If F is not 1 by F is not subharmonic, then we can't get this result, because with this assumption we will obtain this result for both the conditions. But if we remove one condition, then it will be very difficult whether this conclusion does holds or not. Even if there is another strong condition, conformal flatness also.
Dr. Professor Sheikh, there are two more questions on the YouTube chat.
Yeah.
One gentleman asked, sir, please suggest some reference books for the geometry of Ricci solitons.
Yes.
Any book you would suggest for Ricci solitons, geometry of Ricci solitons?
The book itself, this Hamilton book is very nice. That I have given in the reference, and also that survey article by Cow. That is a very nice article. The whole thing is given. The whole development is given. It's in this slide. I'll show you.
And there is another question from Dr. S. Srinivas Rao. He says, fine presentation, sir. Are there any videos to give preliminary facts?
Yes, sorry, please tell me.
Are there any videos to give preliminary facts? some preliminary lectures. Could you suggest some lectures on the YouTube or on the net where they can get some preliminary information on this area?
I don't know, but certainly there are certain videos maybe in YouTube, maybe some lectures from Princeton or other institutes, but I don't know. Yeah, this is a nice article. Reference 6, recent developments on Hamilton's Ricci flow. And this is a nice article, survey in differential geometry. And this article also 7, the whole survey is given here. And you can see the book of Hamilton. Yeah, this 24, the Ricci flow on surfaces and general relativity. And also this another surveys by Hamilton in reference 25.
Dr. Srinivas Rao asks, slide gives definitions of linearity. So is it not asymptotic but local?
Yeah, please tell me which linearity?
The definition of linearity. I think he's referring back to the same slide where you were just shown. Linear volume growth.
Yeah.
So he's saying the slide gives definition of linearity. So is it not asymptotic but local?
Yeah. Actually, yes. Actually, this whole is given in this paper. I just picked up the results because due to this time I have to finish this. That's why the whole thing I'm trying to share this paper. Paper published in Journal of Geometry and Physics. The whole thing is given here.
Okay, so let's thank Professor Sheikh for an excellent talk. And we now go to the next speaker, Professor Mohammed Belkafla. He'll be speaking on the study of Ricci pseudo-symmetry of K-mu spaces. And I'll give a very brief introduction of our speaker. We have very eminent speakers, so I'm very sorry that I'm making the introduction very short because of the paucity of time. Professor Mohammed Belkafa is from Taiba University, and his academic qualifications are as follows: Magistrate in Mathematics from University d'Orléans, Algeria, PhD in Mathematics from Couliban, Belgium University in differential geometry. His research interests are geometry of submanifolds, structures on submanifolds, pseudo-symmetry in R. Dezes senses, Thurston geometry, geometry of manifolds with density. He has rich administrative experience too. He was the director of Laboratoire de Physique Quantique de la Matière et de la Modernisation Mathématique from 2007 to 2013. Head of the group of GA, Geometry and Algebra. He is responsible for Master's Magistrate Geometries de las Variants, Geometry Non-Commutative and Applications. He was in charge of area of mathematics and computer science. And he has over 45 publications. He has attended over 39 international conferences and workshops. He has many publications of reputable journals. So now over to you, sir, for your talk on the study of Ricky pseudo-symmetries of K and new spaces.
Good morning. Assalamu alaikum. Please, I need to share the slide, but it's not possible. I'm trying to. First of all, I would like to thank organizer for this opportunity to talk, namely for my friend, Dr. Majid, and others. I'm very happy that to meet online my friends in different parts in this and the world. So, and also I would thank a very special thanks to my colleague Adila for her main support during, and Professor also Mihai for during the last years. I have a problem to share. I don't know why host disabled participant screen sharing. So give me the authority that I can share. It's possible. Give me the access to share my document, please. Anyway, we're starting now. So for my talk is now about is related to Camus structure that is in complex and very cheap pseudo symmetry. Okay, so we try to share with first. No, not yet. Anyway, for the Camus structures, I should mention that Kochmas introduced the notion, and she introduced the notion, and according to the Riemann curvature, K, X, U, and V, which is the normal bundle of the structure, is 0, and after the homothetic deformation, no, it's okay. Yeah, it's okay. Yeah, sure. It's okay now. It's clear. Oh, sorry, it's clear. It's okay.
Yeah, you can go into the presentation mode, sir.
Okay, good. So I'm saying that, and also after the homothetic deformation, so we get the curvature, and for that reason, this is the motivation she introduced this notion. I mentioned also a nice work, homogeneous and local symmetric of complex Camus spaces by Blair and Adela Mihai. Also, another work is by Uldin. Yeah. And had an dream, and they studied this notion. Okay, but the last we can say I got another paper of Kochmas, which is very, very important for us, a symmetric and complex contact manifold, because she showed that all stronger. She gave, we can say, the symmetry of the Riemann curvature, but for all x for all vectors in horizontal band. Okay. Yeah, I think this is more or less introduction related to the papers. So here, if you see that is an if this is 0, so by homothetic deformation, we can get the Riemannian curvature written in another way. Okay, so this is a structure here. There is a complex contact structure on this product, and by homothetic deformation, you can get the structure. Okay, and I said Blair and Mihai prove the complex Camus with K is less than 1, because for K is 1, we have the normal structure, and locally homogeneous for K minus 1. They prove that is to stability, symmetry, and pseudo symmetry of the structure. Okay, yeah. Let me just to start with the basic notions we need it for later. So we have Riemannian and semi-Riemannian manifold. So we have connection, and you have Riemann curvature, Ricci curvature, and you have the wedge written in this way. And the idea is to see the action of the Riemann. We know that the action of Riemann operator acting on a tensor algebra as derivative, and it's commute with contractions and so on. So if you have T0K tensor, so the action of R on this tensor is 0K plus 1, the same for the action of the wedge on this tensor. Right. Now, this is the way how you compute the R dot T, which is means Rx and Y, this, acting on T. So you can write it in this way. And the same action of the wedge on tensor 0K. So here, for example, if you take T, for example, Riemann curvature, so we can get R dot R, for example, 0, which is semi-symmetric, well known, and there is classification by Szabo. And here, the same for if we take rho as Ricci curvature, so it's called, when 0 is called Ricci symmetric. And there is a relation, yeah, and this also, I'm just to say that in Richard Dash sense for the pseudo symmetry later, yeah. Why? Because first of all, for complex, for real case, yeah, it's a long historic that for the symmetry or the semi-symmetry, as Takashi proved, is always, we can say for the key is 1, is always, you can say, stronger structure. All right. Except I think what we proved that second space form is a pseudo-symmetric and Richard Dash. Yeah. Now, if it's we have this relation between two tensors, so it's called here Ricci pseudo-symmetry in sense of Dash, and in this rho minus S, which is a scalar G non-zero, because if it's 0, which is an Einstein. Okay. Let me introduce the structure, complex structure, which is an two-dimensional, 2 and minus 1 dimension of complex manifold, and you have the covering. This is the holomorphic one forms, and if this form satisfies this condition, so there is no integrability with no, it's far away to have integrability, so it's satisfy the condition, and also between two neighborhoods you have this transformation. Okay. Yeah, here the horizontal bundle, which is all x such that the form is the form apply on x is 0, and the completed of this bundle is the vertical bundle. Just we showed that x and y v in C cross CP is all 0. Okay, the complex counter manifold, as we saw, almost complex structure, so this is compatible between, so we have complex manifold, so we have almost complex structure. So is as for real case, so here you need to two forms, so we have U and V, which is UG, and they are one tensor, not as the real case. So we have here two tensors, such that G and GH, we can say it's called H or not an H. So we have a vector field U and capital U, capital V, which is by the G, say the relationship between LU and V, yeah. And this relation is, we can say, the same more or less as the real cases, as that the square of the tensor is minus identity and plus the form tensorial U and V with tensor with the vector. And also the anti Gx is minus Gx and Gy. Yeah, and the form, yeah, the form of apply U, apply an X, just a G Ux. And this is the relation between a structure G and the answer G, capital G. So we have G is minus G and J. And so you have here Gu is 0, the same for Yeah, if in addition you have that du x and y is exactly gx and the metric apply for x and jy, and the same this for gh x and hy with dv, so that x and y are in an horizontal bundle, then has contact metric structure. So with this is we can say the compatibility between the structure, the metric and the almost complex structure. Yeah, very important answers here because we are trying very important for the structure. Asymmetric tensor HU and HV. This is this notation means symmetrization for the PTPM in horizontal, and you have P, which is the map of PPM in H, the projection show, and you have this is relations satisfied by this tensors H, U, and HV. And first remark, as for example, in a real case, derivative of RAB vector, RAB. So here for the case of, we can say in the complex structure, you have this buffer. Yes. Important point by about normality. If you have complex manifold, contact manifold is normal. This is in Korkmaz definition in another way, because Ishihara and Onichi defined another structure, but we cannot, I mean, have Heisenberg as a central example, complex Heisenberg example, and this is Korkmaz modified the work before. Yeah, and you have this is an S, this tensor, and a capital T, another tensor, and here an homogeneous tensor for G and H. If M is normal, so we have H, U, HV 0. Okay. Now this is if you have this almost complex structure or contact complex structure, metric structure, complex contact metric manifold, and M is called CAMU. For this reason, CAMU is curvature satisfies this relation. Why? Because we know that X, U, and this is on a product of C by CPN, and it's what I say 0 up after deformation. She proved that it's the motivation to define these spaces. Okay, and we have this form. Yes, with this relation that gamma is d sigma. Now, remark that, yeah, also on her paper, she determined all the remaining curvature is determined. Okay. Now, here it's a remark that for complex Kami space, so we have k is minus 1 plus is less than 1 or equal 1. If k1 so H is normal, k less than m is Hadmite 3 orthogonal integrable distributions according to the eigenspaces of H. So to that, lambda is square root of 1 minus k. We here is about the unit horizontal vectors. So kx we can say u sectional curvature and v sectional curvature, as for example for real case we can say kx xc, which is x is a RAB vector. So we have this relation according to x is has a lambda or minus lambda. The sectional curvature spanned by x and y, so we have it here. According to x and y, if they are in the same eigenspace, or if they are in different eigenspaces. Okay. First remark, very proved by this is very important remark, theorem of Korkmaz proved that in her papers curvature properties of complex contact. Okay. She proved that if HU and HV is they are equal, so if this condition, then M is locally to the product Cn plus 1 by Cpr with the holomorphic section of 16. Okay, very remarkable theorem. Okay, so and here it's lemma. It's that for relation between unit vector, we can say gx and gy holomorphic and x and y. So we have this is a relation that they are the same. Yeah, we need this lemma because yeah, for our proof that. So if you have here E I and G E I and J E I H E I and U V, so this is an orthogonal basis with EI and GI are in the same again space, GEI, HEI are in the same space. Okay, so we have here this is the relation of, we can say, sectional curvature, different type. Now proposition, the Ricci operator is given by this formula. Yeah, we need it because, and the Ricci is given by this formula, the last one. Why? Now it's important for us, and we said, and as we did this constant scalar. Very remarkable here. The complex Camus spaces has a constant scalar curvature. This is very remarkable remark. The Ricci curvature is given by this formula 8. So now we are trying to act the connection on first question is can we have Camus space, Einsteinian space? Another thing is possible to get that the nabla rho 0 or the action r x and y dot r 0 and so on. First remark here at the first result that we prove that is not Einsteinian. Yeah, the proof is just to write rho as we can say function f g, and after that using properties of curvature, and we can yeah, if we assume that he's an Einsteinian, we get contradiction. Okay, there is a proof, but just to have more time. So if anyone can, I mean, yeah, we can talk, I mean, by chatting or by mail about the proof. Yeah, I don't know if I can see that. Just to, I don't know if I can share it. Okay, I stay in the same file because otherwise we will have a problem. Okay, now the lemma here, yeah. Now we are sure now for k minus 1 is not Einsteinian space. Just remark for k1, just remark for k1, I should mention some works related to this. First of all, is about if it's normal complex Blair and Mihai proved that local symmetric normal complex space is locally isometric to CP2n plus 1 with holomorphic sectional curvature 4 with the Fibini stereometric. Okay, this is, and also yeah, Blair and one moment, sorry, yeah. I try to see my notes. Anyway, okay, there are, I mean, works related to these structures, namely for K is 1. Yes. With Molina also, they about Vi conformal, and they showed that it's not possible for a normal complex manifold to be conformally flat. And this is, yeah, Molina and Blair Molina proved that the normal complex manifold that are buclar flat must have constant holomorphic curvature 4 and to be also color. And they showed that is not possible for normal complex contact manifold to be conformally flat. Okay, we have a work on this direction related to this, and we proved that for normal complex manifold to be Ricci symmetry, Ricci semi-symmetric, if only if it's an Einstein, or also for complexes GHS sectional curvature constant, we say complex contact space form is to be Ricci pseudo. So if only if C is -1 and L is 1, and we give an example of the properly Ricci pseudo symmetric. This is on the work of Asian European. Okay, yeah, this is okay. And now for this, yeah, we compute this the action of the nabla on rho. So we have this is, and now is the what I say. Pardon. The next result. The next result is if you have complex Kami spaces, so the KNS one is Ricci symmetric if only if is locally isometric to this product. CN+1 and CPN 16 is the same more or less in normal complex structure. CPN is very important. CPN with for holomorphic curvature, sectional curvature. So this is that. Yeah, we can say. I mean, we have only this case. Now, for the next property, we need this lemma, which is technically just to see. Yeah. Okay. So now, for this lemma, you see that G acting on rho 0, this is third remark. The wedge product of horizontal, vertical U and cross V is 0. This is second remark. Third remark, the action of RUV dot R is 0, and RUX and dot is this relation. Okay, and the same for RV and X dot rho is called in this relation. Okay, yeah. Now, okay. Now we are ready to give this remark. So this theorem say that they say that if you have complex Kami spaces, K less than 1 is a Ricci semi-symmetric if only if M is locally isometric. See that is in we know that is the locally Ricci symmetry is Ricci semi-symmetry. So now we can say the inverse. So we have always as Ricci semi-symmetric is only M should be locally to the product. So now it's the last about Ricci pseudo symmetry of this structure. So this last theorem is complex Kami spaces. K is -1 is Ricci pseudo symmetric. Yes, in that sense, if only if is locally isometric to this product. So there is no proper Ricci pseudo-symmetric K-mu. This is, I mean, very remarkable. I found that Korkmaz, as I said, in in 2017, proved that for the symmetric of Riemann curvature, which is, I believe that for Ricci should be that if we Kami space of K is less than 1, and for horizontal vectors, so we have the action nabla WR for all is 0, such that W is horizontal, which means nabla R, nabla WR, we apply X and Y, and Z is 0 for what? For all X and Y and Z and W horizontal vector field, which means this is in adaptation of she showed that is we can say is natural, we can symmetric in this sense. Yeah, another thing is remark for last work of Korkmaz that she wrote this is what I really appreciated. She wrote the complex curvature of Kami spaces in other form, very simple form, we can say. This is work is in published in her in a Haiti Journal of Science and Engineering. I mean, in Turkey. Okay. So here, so we are now we answered all the questions for this talk. So and we said that is complex Camus spaces is Ricci pseudo-symmetric if only if Cn plus 1 cross Cpn 16 holomorphic curvature. Yeah. Remark about Camus, some remarks about Camus spaces is one, if you have Camus spaces and you make another time H holomorphic deformation, so is always you get what I say another Camus structure. Namely, the K, we can say tilde is K plus alpha square minus 1 by alpha square. And mu tilde is mu plus 2 times alpha minus 2 by alpha. This is very remarkable. Another just remark that is for complex Heisenberg, we know that it has a normal structure and K is 1 and mu is 2. So for example, books are variant. For books are variant, we have a books are variant is 1 minus mu by 2 divided by square root of 1 minus K, which is not defined for Heisenberg. This is a remarkable remark. And invariant books invariant for this product Cn plus 1 by this is 1. Yeah, and this is based on namely the book. Okay, the book of Mr. Professor Blair, and also the work of Blair and Mihai. Nice paper, and also about Richie, also about our friend Richard Dash, and also this paper, and Korkmaz here about curvature property and normality, namely for normal, but this is for this is here you see the condition about nullity condition where she gave the information about what they say about Camus spaces. And I think yeah, because I found another paper of her and should be there in the paper, symmetric and complex contact manifold, and the Haiti Journal of Science and Engineering published on 2017. Yeah, I think it's very important, and I think it's another. Yeah, I think it's possible to study different what I say different properties about pseudo-symmetry type, namely, for example, Weil pseudo-symmetry, any tensor acting by Riemann curvature or other tensor. Thank you very much for your attention, and I am waiting for if we have any remarks or any. Yeah. Okay. Thank you very much, Professor.
Thank you, sir, for an excellent talk. Now it's open for discussion. So if there are any comments, any questions, feel free to ask Professor Belkafar. People online can post their questions on YouTube or in the Zoom chat.
Yeah. Okay. Professor Belkafar. Yeah.
Yes.
This is Professor Sheikh.
Yeah, marhaba. Okay, Sheikh.
So your lecture is very nice.
Thank you.
As you mentioned, this Ricci pseudo-symmetry by days, and this slide also shows there is the equivalency between the Ricci pseudo-symmetry and this semi-symmetry. Okay, And
Yeah.
this connection basically is done by Richard Days.
Yeah, it's well
paper
known. Is well known. Is well known as the relation between. Okay. The question about the structure, what is?
Yeah. My question is, you state this theorem. You obtained this theorem. The Ricci pseudosymmetry, if and only if some product, okay, with the complex place and complex projective space. So can you connect or can anyone connect with this Ricci pseudosymmetry by replacing the semisymmetry? Since Ricci pseudosymmetry is equivalent under certain conditions with semisymmetry. So if we replace in case of Ricci pseudosymmetry by semisymmetry, then what will happen?
Look, yeah, a remark, very simple. Yeah. I think for people working on a pseudo-symmetry, Richard Dash or Weil pseudo-symmetry and so on, is well known that is Ricci semi-symmetry implies pseudo-symmetry inversely is not, and in literature there are many nice examples. This is one. Second one is there is a relation between the Ricci pseudo-symmetry and the Ricci pseudo-symmetry, and the inverse is not the same, and so on and so on. So in many papers of Richard Dash and others, we can find many examples about this literature, about this notion. Yeah. But for work, for example, about Camus and so on, there are less examples, less work, and so on and so on. I appreciate work Blair and Mihai, Adila Mihai, and also the very nice work about Korkmaz, namely the last one. Yes. Thank you very much.
Thank you.
Yeah.
Are there any other questions?
Good morning.
Yes.
I am Yon Mihai.
Thank you very much.
Good morning, Mohammed. Good morning, everybody.
Good morning. Thank you very much. Yeah.
It is a very nice conference. In particular, I congratulate Mohammed for this very interesting talk. The subject, the topic is very difficult. Normal complex contact manifolds, and for this reason that there are not so many papers in this field.
Yeah.
And this is another point for Mohammed, that he investigate an modern topic and very difficult. So congratulations again. The talk was very interesting and the results are deep.
Thank you very much.
Thank you. That's all that I had to say. All
Thank
the
you very
best
much.
to all participants.
Thank you very much for nice words.
Thank you, sir. It was an excellent talk.
Thank you very much.
And I don't think there are questions on the YouTube, except for praises from people that it was an excellent talk. Some of them would like to have the PowerPoint presentation if it's possible.
Sure. Yeah,
so if you can share it with the convener, we'll make it available for all.
Thank you very much.
So let's thank Professor Belkar Kilfab Mohammed for an excellent talk. And now we move on to the next talk. We have Professor Zafar Ehsan with us. He'll be talking on Ricci solitons and the space-time of general relativity. Professor Zafar Ehsan is a well-known person in India and in Mano especially. But for the benefit of our international speakers, I would like to introduce him. Professor Zafar Ehsan, he obtained his bachelor's, master's, and PhD degree from Aligarh Muslim University. He got his PhD in 1979, and then he joined Aligarh Muslim University Department of Mathematics in 1978 as lecturer, and later became the reader there in 1992 and served as professor from 2000 to 2016. He also served as the chairman of the department from 2012 to 2015. Professor Zafar Hassan is recipient of many awards. He is the recipient of the Distinguished Scientist Award 2020, Asian Education Award 2020 for contributions to education community, Lifetime Achievement Award in 2019, Nishan Azad in 2017 for promotion of science in Urdu, the International Einstein Award for Scientific Achievements 2011, Rashtriya Gaurav Award 2007, Shiksha Ratan Puraskar 2007, and the Best Citizens of India Award in 2006, 2007, and 2008 consecutively. He is a life member of Indian Association of General Relativity and Gravitation, Calcutta, Mathematical Society, Indian Society of Industrial and Applied Mathematics, Industrial Mathematical Society, and Tensor Society of India. He is the founder member of International Electronics Engineering Mathematical Society, Egypt. Professor Hassan's achievements have been listed in Marquis Who's in the World, USA for 2011-15. His current research interests, apart from general relativity and gravitation, is on Quran, science, and modern cosmology. Professor Hassan has traveled across the globe. He has visited and delivered talks in Tabriz, Iran, in Malaya, University of Malaya, Kuala Lumpur, in Malaysia, International Islamic University, Kuantan, Malaysia, University Science Islam, and in Lucknow, and the list goes on. So I would not come between you and the speaker. Before I part, I would mention that his book on differential equations was very well taken, and a lot of students have benefited from his book, which was published and was the bestseller in 1999. So over to you, Professor Zafar Hassan, Ricci solitons and space-time of general relativity.
Thank you very much, Professor Hassan. It is again nice to see all of you again. I was supposed to be there for quite some time, but unfortunately, things didn't happen in my favor. But anyway, so it is nice to see you again on this platform. So thank you very much for calling me to your conference. I'm always with you. Whatever arrangement you want with me, I'm always with you. So thank you once again for calling me. Anyway, so as stated by Professor Hassan, that my title of the talk is Ricci solitons and the space-time of general relativity. Okay, so I will do with the slides. Is it now okay? Is it visible?
Yeah. Yes, we can see it. Yes.
All right. So now, present. So the basic definition and the recent development in Ricci soliton has been already done by Professor Afsos in his talk. So I will just briefly go through them. Well, this is the plan of my lecture. First, I will give you that why we are interested in studying Ricci solitons, some sort of a motivation. And then the definition of the Ricci fellow and Ricci solitons. Next is I will talk about the symmetries of the space-time and how and which type of role Ricci solitons are going to play in the study of these space-time of general relativity. And in particular, we will deal with two special type of space-times, the type D and type N pure radiation field in context with the Ricci solitons. And finally, we will try to find out the corresponding solitons for Schwarzschild exterior solution and Reasoner-Nostrom solution, which are very familiar solution in the field of general theory of relativity. So Ricci flow, as discussed by Professor Apsos, it was introduced by Hamilton in 1982 to study the compact three-dimensional manifold with positive Ricci curvature, and he calls equation defining Ricci flow as evolution equations. So without going into the much detail that how it got into the picture, I will simply come to the point that the concept of Ricci soliton was introduced by Hamilton in 1988. Okay, they are the natural generalization of the Riemannian metric, or rather the Einstein metric, which have been a subject of intense study in the differential geometry and geometric analysis. So Ricci soliton, they are the geometric fixed point of Hamilton-Ricci flow. So during the last few decades, number of people have done about Ricci soliton with in the context of differential geometry. For example, C.K. Bagewali, UC Day, Apsos, Arindam, Narasimha Murthy, S.K. Hui, Hassan Shahid, Nagaraja, Sharif Deshmukh, Abdul Hasib, Danish Siddiqui, and their collaborator. They have done a lot of work on Ricci soliton and their generalization in the context of differential geometry. So motivated by this role of Ricci flow and Ricci soliton in differential geometry, in this talk, let us see what role is played by Ricci soliton on the space-time of general relativity. So Ricci flow, it is defined in this way. It is satisfying the partial differential equation delta Gi upon delta T equal to -2 times Rij. Rij is simply the Ricci tensor. So this equation one can consider as the heat equation for a Riemannian space. So the immediate consequence of this equation is Ricci flow equation is that if I take this right hand side to be 0, and when Rij is 0, we call the space as to be a Ricci flat, or the empty space time, as we say in general theory of relativity. So then we will have delta Gi upon this side is 0. So this means the partial derivative of G is going to be 0. This means the Ricci flow leaves the metric unchanged. Conversely, any metric unchanged by Ricci flow is Ricci flat. So in differential geometry, Ricci flow is an intrinsic geometric flow, that is a process which deforms the metric of a Riemannian manifold. So in the lecture of Professor Sheikh, after the lecture of Professor Sheikh, somebody asked that can we have some sort of a film or video on this Ricci soliton? So of course there are few videos which are available on the net. On YouTube you can go and see that these Ricci flow, they are simply nothing but they are deforming the metric. Okay, they are changing the metric of the Riemannian manifold. How the metric is going to be changed, or they are deforming the metric or changing the shape of the metric. So this is the main role. So it is some sort of a diffusion equation. So we define a soliton like this: a solution of an evolution equation that evolves along symmetries of the equation is called a soliton, or simply a self-similar solution. So by self-similar solution, we know what is a self-similar solution. Simply we have given a different name, and the name is the soliton. So if we imagine the Ricci flow as the flow of some vector field on the space of matrix, then the soliton may act as an attractor to this flow. In case of two-dimensional sphere, the flow is known to converge to a soliton. So in differential geometry, what we mean by the Einstein metric? So Einstein metric, it is defined in this way. So a Riemannian metric which satisfies this equation: Rij equal to lambda times Gij. So where lambda is equal to R upon n. R is the scalar curvature. So which is defined again in terms of the Ricci tensor and the metric tensor. So if we take lambda, this thing to be the R upon N, then this Einstein metric, this will become the Einstein manifold. So we have a Einstein metric defined in this way. So now we have the definition of Ricci soliton. So once this thing we have got, Rij is equal to lambda times Gij. So we have got a Einstein metric. So Ricci soliton, they are simply the generalization of Einstein metric in such a way that if I add something here on the right hand side, if I add half Lie derivative of Gij, then this will define a Ricci soliton. The same thing I have written in this way. Rij minus this factor is added in this equation. So it is some sort of a generalization of Einstein metric, where lambda is a real number and this symbol denotes the Lie derivative with respect to the vector field xi. Okay, so along the vector field xi. So since we have a constant lambda in the defining equation of Ricci soliton, this will mean that the metric is not fixed by the fellow up to a diffeomorphism, but expanded, contracted by a scalar. Okay, so we have the definition now that the Ricci soliton is shrinking, steady, or expanding. Steady means translating. So either it is shrinking or translating or expanding according as lambda is positive, then it is shrinking, lambda equal to 0, then it is steady, and if lambda is negative, then it is expanding. Gradient soliton is also defined by Professor Sheikh, so no need to go the same thing again. Now there is an excellent review given by this Chow in 2009 that why we are interested. He has given so many reasons from the differential geometric point of view. So now let us see why we are studying, why we are interested in studying the Ricci soliton on a Riemannian manifold. What is the use? Why we are interested? So let us see. First thing is, if a vector field is given, then what is the nature of the Riemannian manifold? This is the one reason. Another reason is that what will be the nature of the vector field if the property of the Ricci tensor are. So with these two motivation in the mind, let's go to our main business, that instead of considering the Riemannian manifold as a purely geometric entity, we now consider this is a space-time manifold of dimension 4. Okay, then some of the immediate consequences of the Ricci soliton equation. Ricci soliton equation we have defined as Rij equal to minus half Lie derivative of Gij equal to lambda times Kij. So if we means that Lie derivative of Gij equal to 0 means that Gij is a Killing vector field, that Xi is a Killing vector field. Lie derivative of the metric tensor is 0 with respect to a vector, then that vector is said to be a Killing vector. Okay, so if Xi is a Killing vector, then simply we have got this equation. And the space-time manifold is an Einstein manifold if we have lambda equal to R upon 4. So another one is that for a steady Ricci soliton, that is when lambda to be 0, then we simply have Rij equal to Lie derivative of Gij. Okay, and this will simply gives you that if Xi is Killing, that if right hand side is 0, that is Xi is Killing, then the space time is Ricci flat, and of course conversely. So we have few remarks that what is the Ricci flat solution of the Einstein field equation is simply the Schwarzschild exterior solution. And this describes the space-time due to an isolated, static, and spherically symmetric gravitating mass. So metric is known to us like this, that ds square is equal to this one. This is the metric of a static Riemannian space. Metric of a Schwarzschild exterior solution. And then we take this lambda in our equation, the equation which define the Einstein metric, lambda is equal to, we take as capital lambda, and we take this as a cosmological constant. Then this corresponding Schwarzschild solution, this will take this form. Only the cosmological solution has been added. Okay, so that when we take m to be 0, m is the mass of the object. So if we take m to be 0 and lambda to be 0, the solution reduces to the flat space-time metric, and the metric is well known in the spherical coordinate dr square minus r square d theta square r square sine square theta d phi square plus dt square. This is the metric of a flat space in a spherical coordinate system. Now, also we know that that if a space has a maximum number of killing vector, then this space is said to be a maximally symmetric space. And once it is a maximally symmetric space, naturally it is a space of constant curvature, and consequently it becomes an Einstein space. So the significance of spaces of constant curvature is very well known in cosmology. So whenever we are going to obtain a cosmological model, we have to make certain simplifying assumptions, and the assumptions are that the universe is isotropic and homogeneous. Isotropic means that in whatever direction you see, all the directions are equivalent, and homogeneous means that the matter throughout the universe is spread homogeneously, is spread uniformly. Although this is not the realistic situation, somewhere you will find out in the universe, somewhere you will find out a lot of matter, somewhere there is nothing. So, but on the large scale, just to model the simplest cosmological model, we have to make certain assumptions. So assumptions are isotropic and homogeneity. Isotropic means in whatever direction you look in the universe, all the directions are equal, spatial directions are equivalent, and the matter throughout the universe is spread uniformly. So this cosmological principle, when we translate it to the language of Riemannian geometry, this says that the three-dimensional position space is a space of maximal symmetry, and of course it is a space of constant curvature whose curvature can depend upon time. And for this we have got certain models already. We have got, for example, we have the de Sitter model of the cosmological of the universe. It is like this. So it is a closed model when this cosmological constant is positive, and it is an open model when the cosmological constant is negative, and it is a flat model when the cosmological constant is 0. Okay. So now whenever we are going to find out the solution of Einstein field equations, since they are a second order nonlinear, highly nonlinear differential equation, so sometime it or most of the time it is very difficult to solve them. So just to make the solution simply in a simple to find the solution of the Einstein field equation in a simplified way, we assume certain symmetry assumptions. Okay, so that will ease our work, that will ease our job. Okay, so we have to impose certain symmetry condition, and those symmetry conditions, they must be compatible with the dynamics of the chosen distribution of matter. So the geometrical symmetry of the space-time, they are often defined through the vanishing of the Lie derivative of a certain tensor with respect to a vector. Okay, so a geometrical symmetry is defined in terms of the Lie derivative. So how it is defined? So the role of symmetry, it was first defined in a paper by Kazin and his collaborators. So he developed the role of symmetries in general relativity through a series of papers 69 up to 77. Okay, so these symmetries, they are also known as collineations. They were further studied by myself and my group, my supervisor, Professor Hussain, and of course our group at AMU. They have developed a lot working on these symmetry properties of this space-time. So far more than 26 different types of symmetries have been studied, and the literature is very large. Of course, it is still expanding. Recently, my students, Bilal, Ali, Salman, and Bilal, they have defined a new type of symmetry called as the conharmonic inheritance, and they have studied it. So here in this paper or in this talk, I will consider there are more than 26 symmetries. So I will take only those which are necessary for our work. So first one is the motion, that when we take the Lie derivative of Gij is 0, the Lie derivative of the metric tensor is 0, then we say that there is a motion. Okay. So motion and this vector xi, they are known as the Killing equations. So Killing equations, they are very important in differential geometry as well as in relativity. As we see that the Schwarzschild solution has got three killing vectors, while radiating star solution has got four different types of solutions. Okay, four different types of killing vectors, the radiating solution of a star. Then we have a conformal motion. Lie derivative of gi is equal to some scalar times gij. So space time is set to admit a conformal motion. A special conformal motion is defined in this way. The same thing here, but except that this scalar has got this extra condition that the covariant derivative is going to be 0. Then we have homothetic motion, and in such case, this omega is simply a constant quantity. Homothetic means that there's the two ratios, the distance of the two ratios, they are constants. And then we have Weil conformal collineation. So Cijk, this is a Weil conformal tensor. So if the Lie derivative is going to be 0, then we say that the space-time admits a Weil conformal collineation. Then we have curvature collineation. Rijkl, this is the Riemann curvature tensor. If its Lie derivative is going to be 0, then the space-time is set to admit curvature collineation. Then we have the Ricci collineation like this. Lie derivative of Ricci tensor is 0, then it is Ricci collineation, as well as affine collineation, that the Christoffel symbol of the second kind, its Lie derivative is defined in this way. If it is going to be 0, then the space-time is set to admit affine collineation. Then we have conformal collineation as well as a special conformal collineation. Okay. So these are the few symmetries that I will need. There are many more that we can do in a similar way. So for example, now we consider again our equation number 3, that is the defining equation of the Ricci soliton. Okay. So for flat space, that is when Rij is 0, then Lie derivative of Gij comes out to be 2 times Gij. Okay. So this is simply a metric inheritance symmetry. So if in this case, this vector field xi, this is conformal killing. Okay. It is a conformal killing vector, which include a homothetic vector and a killing vector according as this gamma has got this condition. If this lambda is 0, then simply we have a killing vector. And if it is its covariant derivative is 0, then we have a homothetic killing vector, and so on. So this is the main one. Now again, if I take, so this is our defining equation of the Ricci soliton. Rij minus half Lie derivative of Gij is equal to lambda times Gij. So if we take, if our this Lie derivative of Gij is 0, that is xi is killing, then this reduces to this one. If I take the covariant derivative of this, then we have got simply the covariant derivative. We take covariant derivative of metric tensor is always 0. So we only have the covariant derivative of Ricci tensor is 0. Thus we can say that we have got a result that if the vector field xi associated with the Ricci soliton is killing, then the manifold M is Ricci parallel. So this is how we can connect the geometry and relativity together. There are many more things. So again, we take the Lie derivative of the previous equation. Lie derivative of Rij is equal to Lie derivative of this one, and we do some calculations. Then we find out that if the vector field xi associated with the Ricci soliton is killing, then the space time, yani if this is killing, then simply we have Lie derivative of Rij equal to 0. That is the space time admits Ricci collineation. Again, we do some calculation with these two equations. This equation, the definition of the killing vector. This is the just in the definition of Ricci soliton. We put down the definition of killing vector field and then simplify it. So we will get this one, that scalar curvature comes out to be theta plus lambda times n. Theta is the expansion scalar. So we thus have a corollary that if the Ricci soliton is steady, then the scalar curvature is expanding. Again, we do some calculations, and then ultimately we got a lemma. So that lemma has already been developed by some other fellow. We need this lemma. So the killing vector field associated with Ricci soliton is conformally killing if and only if M is an Einstein manifold. So from Yano, the book of the Yano, the theory of Lie derivatives, we know these results. Okay? So using these results, if we consider xi as a conformal Killing vector field, then we got a result like this, which I take as a lemma. If xi is a conformal Killing vector field, then it is also a conformal collineation vector. Now combining these two lemmas, we got a result. So the result is a vector field xi associated with a Ricci soliton is conformal collineation vector field if and only if M is an Einstein manifold. And we have already seen that Einstein manifold, they are of very importance in cosmology. When we are developing the cosmological models, we need some Einstein manifold. And those people who are working with general relativity, though, they know that Petrov, A.Z. Petrov, a Russian physicist, has written a complete book on Einstein spaces, showing that how they are important in general theory of relativity in general and cosmology in particular. So they are playing a very nice role. So that's why we are very much interested. Now, if we use the definition of a special conformal motion, then we have got a corollary like this, that if this quantity is 0, then vector field associated with the Ricci soliton is a special conformal collineation vector if and only if the manifold again is a Einstein manifold. Again, we do some calculation with the previous equations, and we got an important result that for Einstein spaces, the vector field xi associated with the Ricci soliton is Killing if and only if it is expansion free. So the expansion is scalar theta is coming over here. So this is some sort of a physics is involved here. So again, we do some calculations, and then we got another result. If the vector field xi associated with the Ricci soliton defines a homothetic motion, then the manifold is Ricci parallel. So again, here we got a geometric result. So now we consider the Weil conformal curvature, Weil conformal tensor. Cij, it is defined in this way, and then from the Yano, we use the result that how we define the Lie derivative of the Riemann tensor. Using these equations, we got an equation. We got another relation or another result that Lie derivative of Weil tensor is 0. That is, it is we are having the, that is the, for the space time of general relativity, every conformal Killing vector field is Weil conformal collineation vector field. So this is another important result. Now, from these lemmas, we can combine lemma number 1, which we have done previously, and lemma number 3 that we have just now. So we got an excellent result. A vector field xi associated with Ricci soliton is Weil conformal collineation vector field if and only if the space-time is an Einstein space-time. So we can have many more results. There are a number of results. I have mentioned only few, that we can deal with the other symmetries also by doing the same type of calculation. And for further details, one can have these two references. This is a recent paper. And then another one is with my student, Musawwar Ali. So now let us see what the role the Ricci soliton they are going to play in the study of two different types of space-time. One is type D, another is type N. So what are these space-time? First, let us see. So Petrov has classified, there are three methods how to classify a space-time or how to classify a gravitational field. For those who has just entered in general relativity, I simply say that if you have any mass and if you put any mass anywhere, a field is produced. That field is known as a gravitational field. So gravitation is a field phenomena. So once a field phenomena is there, this means if you want to study it, you have some field equation. So we have got some field equations. They are known as the Einstein field equation. In the form, in the presence of matter, they are also there. In the absence of matter, we also have the field equations. So the solution of these field equations gives us different types of space-time. Now the Riemann curvature tensor, it is playing a very important role in the classification of space-time. So accordingly, the Riemann tensor has been classed because Riemann tensor describes the gravitational field. If the Riemann tensor is there, this means the gravitational field is there. If Riemann tensor is absent, this means that the space is flat. So that's why for flat space, there is no curvature. Space is flat. So for a curved spacer, how much space is curved? That is defined through the equation of geodesic, and that equation of geodesic is written in terms of the Riemann curvature tensor. So Riemann curvature tensor has been used to classify the gravitational field by Petrov. He classified in a number of types: type 1, type 2, type D, type 3, type N. Type 1 is known as algebraically general. Type 2, D, 3, third, and N, they are known as algebraically spatial. So type D and type N, they are very important classification. They are very important space-time or very important gravitational field, because most of the physically significant space-time that we have our hand, for example, the Schwarzschild solution, the Kerr black hole, or the Kerr-Newman black hole, or the Vidya metric of a radiating star, or the Goodell metric, and so on. All those physically significant metric, they belong to type D. And whenever a space-time belongs to type third or type N, it gives you the state of gravitational waves. So gravitational waves also, they are very important from physical point of view, as well as from mathematical point of view. They are also very important, because we got some special type of exact solution of Einstein equation that gives us the emission of the gravitational waves. So this is just how. So now let us see what the role are Ricci solitons they are going to play to find out the symmetries of the petrotypes. Now, one thing is clear, very clear. One should also take the definition. Rij, definition of the Ricci soliton. Rij is equal to minus half lambda times minus half Lie derivative of Gij equal to lambda times Gij. So in this equation, Lie derivative of Gij is there. So this means some sort of symmetry is already there. So that's why we are interested in studying the symmetry properties of special type space-time, for example, type D and type N, because Lie derivative is involved in the definition of the Ricci soliton. So that gives us the motivation. So a lot of people have done, myself and my student, my group at AMU, they have done a lot of work on this one. So for example, for type D, in pure radiation type D field, conformal motion, spatial conformal motion, and homothetic motion, they all degenerate to motion. So once they all degenerate to motion, so from lemma number 1 and lemma number 4, we have an important theorem for type D space-time. For type D, pure radiation field. So now when we have a pure radiation field? Pure radiation field means gravitational field plus electromagnetic radiation. Then this will give us the pure radiation field. Okay, so we have a pure radiation field. That is, in this field, type D field, not only the gravitation is there, but electromagnetism is also there. So they do admit motion along a vector field associated to Ricci soliton if and only if M is in Einstein space. Another result which we can have, again by using the definitions of the Ricci soliton, the type D pure radiation field, they admit Ricci collineation along a Killing vector field associated to Ricci soliton if and only if M is an Einstein space. So similar number of results we can got very easily, because it is known to us that motion implies almost all the symmetries of the space-time. So while for the type N type, for the petrotype N, the solution, the space-time that represent the gravitational waves. So we have got the type of relations. So I, with my students, they have focused our attention on how the electromagnetism, how the electromagnetic radiation and gravitational radiation, they are going to interact. So some time ago, some 20 years back, I have find out a solution that what will happen if the gravitational waves and electromagnetic waves, they are interacting each other. So what will be the space-time that represents the situation? So the importance was there. So myself and my student, they have find out this one. They focus their attention and find out different types of symmetries. So these fields are known as the pure radiation fields. So for pure radiation fields, we have got these type of theorems. That type N pure radiation field, they admit motion along vector field Xi associated to Ricci soliton if and only M M is an Einstein space. And then from the definition of Ricci soliton, we have similar type of theorem. A killing vector field associated to Ricci soliton is a Ricci collineation vector field for type N pure radiation field if and only if M is an Einstein space. And there are many more theorems that we can find out. For example, we can also have pure radiation field, pure radiation type N fields. They admit affine collineation along killing vector associated to Ricci soliton if and only if M is an Einstein space. Again, from the definition of the Lie derivative of the Riemann curvature, this is a basic definition how we define the Lie derivative of a fourth order tensor. So we have got another result that a killing vector field associated to Ricci soliton is a curvature collineation for type N pure radiation field if and only if M is an Einstein space. And similar other type of symmetries we can find out. Now, just within 5 or 6 minutes I have left still, so I will try to give you some idea that how we can find out the Schwarzschild, how we can find out a soliton corresponding a space-time solution. And the main, the first important solution of the Einstein field equation that was for the empty space-time solution of the Einstein field equation, this was obtained by Schwarzschild. He was but Einstein gave his theory in 1916, more than 100 years ago. So just after 1 month, Schwarzschild find out a solution of the field equation. Although Einstein has also find out a solution, but that method was very difficult. But Schwarzschild has given a very simple method how to go to the solution of a spherically symmetric object which is placed somewhere and it has rest. So what is the field outside that gravitating object? That is, we have got a spherically symmetric mass which is placed somewhere. So since the spherically symmetric mass is there, so we are using the spherically symmetric coordinates. So what will be the field outside this one? So outside the field that Schwarzschild has find out within a 1 month of the theory that was given by the Einstein. And his solution, his method was very, very simple. That was so simple that still we are teaching his method in our postgraduate classes. So anyway, so first thing is that once a Schwarzschild solution is known, how to find out its solitons. Solitons, I have told you earlier that solitons are responsible for deforming the metric of the space-time. So once the metric of the space-time is there, how much it is going to be deformed by the soliton. So that we are applying on Schwarzschild solution and then see what will be the change in the Schwarzschild metric when we apply Ricci solitons on this. So this is how we obtain the Schwarzschild soliton. So minus 1 to the power 1m like this. So under root minus 2 sine over is there. In the original metric, this was not there. So we have the metric is changed. So it is deformed. So that metric is deformed. So using the 6-dimensional formalism, we have find out that depending upon this characteristic equation, we have find out the eigenvalues and so on, and find out this soliton that it is not that Schwarzschild solution. It is observed that not only the Gaussian curvature differs with that of Schwarzschild metric, but also the dependence of curvature on eigenvalues is not similar, that we have seen. So thus the deformation in the metric of a space-time is cause for the change in the geometry or the gravitational field, because the geometry of the Riemannian metric is defined by the metric tensor. And sometimes when we consider this in the geodesic equation, so this metric tensor act as the potential of a gravitational field. So gravitational field is changed or the geometry is changed. Now when we add, so this is the Reasoner-Nosdam metric. So here you see that Schwarzschild solution is there. That is, we are putting a spherically symmetric mass. A spherically symmetric mass is placed somewhere. Okay, it is at rest. This is the simplifying assumption. It is at rest. So what will be the field outside this? This is known as the Schwarzschild exterior solution. Now, if we add charge to the Schwarzschild solution. That is, we put down the electromagnetism to the Schwarzschild axial solution. Then we got the Reasoner-Nosdam solution. So Reasoner-Nosdam solution is given by this one. So where E denotes the charge. Okay. So E denotes the charge. So my student and me, we have developed the Reasoner-Nosdam soliton that corresponding to this Reasoner-Nosdam solution, the soliton has got this form. So now you can very well see the change here. The metric has been changed. The metric has been changed, so it is deformed. So this is the role which is played by the solitons in general theory of relativity. So from here we have two very immediate consequences. If a charge is zero, we have got the Schwarzschild solution and correspondingly Schwarzschild soliton. And M is zero and charge is zero, then we have the flat space-time soliton for the flat space-time. Now, so from this discussion that we have done for the Schwarzschild axial solution and Reasoner-Nosdam solution means that we are adding electromagnetic field to the Schwarzschild solution. So from these discussion, we can see that the solitons are responsible for the deformation in the metric and hence in the geometry as well as the gravitational field. So using the techniques that we have developed in finding out the solitons, it was a paper in the Arab Journal of Mathematics in 2015 with my student. So using our technique, recently Manjuta and Narasimha Murthy and another fellow, they have studied the geometric properties of Bartholdi-Kazner space-time, and they have found out that in Bartholdi-Kazner space-time, every point is isotropic. So, well, that's all that I want to say in this such a short time. There are a few references here. So this is one of my recent books, Tensors, Mathematics of Differential Geometry and Relativity. So most of the tensorial equations that I have discussed here are given in this book. And these are the papers, some of my papers on symmetry business. So that symmetry business I have started in 78 and still the people are continuing this business. So whatever result that we have stated here, they are taken from these papers, International Journal of Theoretical Physics, and then again International Journal of Theoretical Physics, as well as these are the students of my student Musawwir Ali. So they are also doing some work on these symmetries. They have defined a new type of symmetry which they call as semi-conformal symmetry. Again, they have a study in the context of fluid space-times. Recently, very recently, in a very good journal, Universe, Musawwir, my student, and his student Salman, and again my student Bilal, they have defined a new type of symmetry which is known as the conharmonic curvature inheritance, and they have discussed its geometric as well as physical consequences. So this is the paper which is on Ricci soliton. So this is perhaps the first paper on Ricci soliton in the context of symmetry of the space-time. Yeah. As well as not only the first paper, but it was first paper in the first journal. Okay, the journal was introduced in the same year when this paper was published. So some recent work are here. So recently I have published a paper about the Ricci solitons and the general relativity in Journal of Tensor Society. We have a Tensor Society of India. They are publishing a journal. So in that journal, I have a lengthy paper. And this is the paper that how we can get the Schwarzschild soliton. So this has been done by my students. So this is how we can find out the geometry of a charged rotating black hole. Black hole means charge rotating black Schwarzschild solution is simply static. Okay, it is placed somewhere. It is not moving. So most of the stars that we have with us, they are spherically symmetric in nature, but they are not static. They are moving. So if the star is moving, then what will be its gravitational field? So angular momentum, this destroyed the spherical symmetry of the object. So we have, when we add rotation to the Schwarzschild solution, what will happen? We get a curved black hole. or rotating black hole, which is known as the Kerr black hole. And when we add charge to this Kerr black hole, we will get charge rotating black hole. So what will be the geometry of this charge rotating black hole? That has been discussed by my student in this paper as well as in another paper. And this is the recent paper which is based on our work in Arab Journal of Mathematics 2021. And so that's all. Thank you very much.
Thank you.
Thank you very much.
Thank you, Professor Hassan. It's always a pleasure to listen to you. There are some lecture questions.
Sure.
Tahir Manzoor asks, sir, in one of your slides, you have mentioned about vanishing Lie derivatives of certain tensor. So which tensor you have taken in your presentation whose Lie derivative vanishes?
So I have defined a lot of symmetries. Most of all the symmetries, they are defined through the vanishing of a certain tensor. For example, if the metric tensor, you consider the metric tensor and its derivative, Lie derivative is going to be 0, then we say that this defines the motion. Okay. That is, if things are moving along certain congruences against certain curve, then the distance is always preserved. Okay. This is what we mean by the symmetry or isometry, what we call Lie derivative of Gij. Then this xi along which the Lie derivative is defined, this is known as the killing vector field. This is one symmetry. Another symmetry is that if I take Lie derivative of Gij equal to some constant times Gij, then we have homothetic motion, or we have got conformal motion, and so on. Okay. If we take the Lie derivative of Riemann curvature tensor to be 0, then we have the curvature symmetry. Okay. If we have the Lie derivative of Weil tensor to be 0, then we have the Weil conformal collineation or Weil conformal symmetry. And if we take the Lie derivative of, suppose, Ricci tensor to be 0, then we have a Ricci collineation or Ricci symmetry. So it depends that which type of symmetry you are taking. So most of the symmetries, or almost all the symmetries of the space-time, they are defined through the Lie derivative. If they are going to be 0, then we have certain type of symmetries. Okay. And if they are not going to be 0, for example, if we consider Lie derivative of Gij equal to some constant times Gij, the right-hand side is not 0. So whenever right-hand side is not 0, then we have a symmetry inheritance property. So in this case, when Gij is equal to lambda times Gij, then we have metric inheritance symmetry. Suppose by this Gij, I replace Gij by, suppose, energy momentum tensor. That is, I consider the Lie derivative of energy momentum tensor equal to some constant times energy momentum tensor. Then this will be the energy momentum tensor symmetry inheritance. Okay. So we have two type of symmetries. One is the simply their Lie derivative is going to be 0. Other is it is not going to be 0. Then we have symmetry inheritance. Yes.
Thank you, sir. There's one more question by Tahir Manzoor. How far does Ricci solitons be used to determine gravitational waves?
Oh, gravitational waves. So that aspect I have not seen yet. I have simply told you that solitons, they are responsible for deforming the metric of a space-time. Okay. And what these black holes they are doing, they are simply deforming the space. They are changing, they are warping the space around them. So a gravitational object which is changing its space around them. For example, if you consider pulsars, binary pulsars, if you consider them, and they are rotating around each other. So by their rotation, some waves are emitted. Those waves are known as the gravitational waves. So these gravitational waves, they create ripples in the space-time. Okay. And of course, they are changing the shape of the space due to that ripples. Okay. So that shape one can apply. I have not yet applied it here. I have not yet applied solitons in the case of gravitational waves, but it may be, it's my feeling, because gravitational waves, they are simply the ripples. Just when you throw a stone in the pond, some sort of ripples are there. So when these binary pulsars, they are rotating each other, so they create ripples. So those ripples, they are nothing, they are traveling with the speed of light. They are the propagation of gravitational waves are there. So these ripples, they are changing the shape of the space-time around there. Okay, so maybe since solitons, they are responsible for changing the geometry or changing the gravitational field, so maybe they can be used. I have not yet seen that. Maybe the people are there, relativity people are there. I have started this business so the other people can try. Some of my students, they are trying to do it. They are applying it. But the main thing nowadays is that the people who are working in differential geometry on VAR products. So VAR product people, they can apply their geometric techniques to the black hole physics. Yes.
There's some crosstalk. Basically, Tahir Manzoor is working on Clifford algebras and applications. So he's trying to look into various aspects of how they can be applied. Okay, so thank you, sir. Before we, there are no questions on the YouTube. There are many people who have praises for a nice presentation, and many want to have the PPTs of all the speakers. So if those speakers who are ready to share their presentations, please give us the permission so that we can share it with the participants.
So one thing I will say that there is a reference in my PPT. One of my paper that appeared in Journal of Tensor Society 2018. So that paper contains all the results that I have presented here. So people may see that paper. Everything will be there. Of course, some derivation will also be there. In PPT, you can't find out derivations.
Mohammed has raised his hand. Mohammed, may I know, I can't see the Danish Siddiqui. Mohammed Danish Siddiqui. Yeah, you can unmute and ask your question.
Yes, sir. Thank you, sir. Sir, actually, there is a situation for Einstein equation in purely electromagnetic distribution. There is a relation for this, the distribution equation. So, sir, this equation with the Ricci-Soliton, so can we deal with these two equations?
No, you want to replace Lie derivative of Gij with the electromagnetic field tensor.
Yes, sir, with these two equations, I want to find something.
You can't do that. Mother, it's my feeling because you see, Ricci-Soliton equation, it is defined by Rij minus half Lie derivative of Gij equal to lambda times Gij. Okay.
Yes.
So two tensors are involved here. One is the metric tensor, another is the Ricci tensor. Both of them are symmetric tensor. So if you replace this Gij by electromagnetic field tensor, which is anti-symmetric, so you can't do that.
So, but sir, can we insert the Ricci-Soliton here in this thing? It's possible. In place of Ricci tensor. So can we use this Ricci tensor in this equation for a magnetic equation?
No. Both the sides should contain the symmetric tensor or anti-symmetric tensor. This is the basic thing. Okay. So you have to equate the degree of freedom also, now.
Yes, sir.
No, so that's why both the sides have the similar types. And you are adding two tensors. For example, Lie derivative of Gi, this is a tensor quantity. Rij is a tensor quantity. You are adding two tensors. The result should be the tensor of the same nature. Nature means they must be covariant, or as well as they must be symmetric. So you can't do the anti-symmetric type of thing. But anyway, you can replace it by another Tij. There are so many Tij which are
other tensors.
You can take the Tij of perfect fluid. No matter that. Only the calculation will be difficult, but you can do that.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you, Professor Ehsan. Before we move on to the next speaker, may I request everyone to switch on their cameras. We'll have a screenshot. So please switch on all your cameras. And Dr. Subhash, can you please take the screenshot?
Yes, sir.
Professor Sirajuddin, sir, can you please switch on your camera?
Morning, sir. Actually, I am using computer, so there's no question.
Okay, okay. Maybe Subhash sir, we can click now. Professor Sirajuddin, sir, can you please switch on your camera?
Actually, I am
So you can see that there are a lot of students who are sitting in our seminar room who are listening to the talks on the this being projected on the screen, and they are posting the questions in the YouTube or on this chat, Zoom chat. So thanks a lot. We shall now move on to the next talk. The next talk is sitting in a seminar room who are listening to the talks on the is being projected on the screen. Somebody is. Yeah. Thank you, Professor Hassan. Thanks a lot for the lovely talk on Ricci solitons and the space-time of general relativity. Thank you.
Thank you very much.
So our next talk is, and the last for today's session is by Professor Sirajuddin. He'll be speaking on recent developments on slant submanifolds and their applications. A few words of introduction of Professor Sirajuddin. He is presently at the Department of Mathematics, Faculty of Science, King Abdul Aziz University, Jeddah, Saudi Arabia. Professor Sirajuddin obtained his master's degree, MSc, MPhil, and PhD degree from Aligarh Muslim University. He has been guest faculty at AMU. Then he went to University of Malaya in Malaysia. After that, in 2014 to 2016, he was assistant professor King Abdulaziz University. And he was associate professor at the same place from 2016 to 2019. And 2019 onwards, he's a full professor at the King Abdulaziz University. He has supervised postdoctoral and PhD students, as 4 people have been awarded PhDs under him. He has a host of publications in international and very prestigious journals, and a list of articles in Scopus journals. He has attended conferences and made presentations in Malaysia, in the Czech Republic, in Turkey, Thailand, Indonesia, Cambodia, Saudi Arabia, United States of America. And I request him to, before I end, I would like to say that he is the life member of Mathematical Reviews, AMS USA, life member Cambodian Mathematical Society, life member of South Asian Mathematical Society. And with this, I request him to give his talk on recent developments on slant submanifolds and their applications.
very good morning to all of you, and those are in India. Very good afternoon. Sir, can you hear me?
Yes, we can see your slides and we can hear you.
Okay. That's good. So, the title of my talk is, as you said, the recent development in slant submanifold. So, actually, the slant submanifold introduced by Bang and Chen in 1990. After that, then huge evolution come after his paper published in Bulletin of Mathematical, Australian Bulletin of Mathematical
So it has a lot of applications, blend submanifold. Before that, CR submanifold and holomorphic and totally real submanifold is studied in almost solution and almost technical manifold and locally productive manifold. After the definitions of blend submanifold, many other submanifold defined, like using the slant, one of the slant distributions. N. Papaguik in 1994 introduced semi-slant submanifold. After that, WGO and Sergio studied hemi-slant and bi-slant and some other sort of applications. So, slant submanifold actually have in different directions applications. It has different applications, like Professor I. Mihai and Adela Mihai both are there. So they study, they use slant submanifold by to prove the chain Ricci inequality. So this is one kind of application. Another application, BY chain himself and many others, they studied existence and uniqueness theorem, and itself it has many applications like existence and uniqueness theorem in complex spacetime and contact spacetime. Professor Ram Shankar Gupta, he worked in existence and uniqueness theorem in contact mechanism, and BY chain as collaborator, Professor Mihai and others, they did existence and uniqueness theorem in complex, almost almost complex manifold, as well as in context of contact. So another generalization of blend submanifold, Bang Chen and Ozegare, actually before that, Itayo, Fernandez Itayo studied the blend submanifold, that the function is not constant. And function is a theta, that the angle is not constant, it is variable. So he defined slant quasi under the name of quasi slant manifold, that the function is not constant. Okay. So later on, very recently in 2012, the Bang Chen and Ozegare used a point-wise, they call it point-wise semi-slant, and they have many applications, and also some examples in Euclidean spaces. So here, actually, there are, as I told you, that there are different contexts. So I'm just studying here the slant submanifold of locally product Riemannian manifold, neither in almost complex or neither in context. So in case of almost product Riemannian manifold, Shahin and Mehmet Echkin and some others studied slant submanifold, and then on the line of Bang and Chen, Ahmad Gulbahar also and Gaspar studied slant submanifold, point-wise slant submanifold of almost product Riemannian manifold. Very recently, using this notion, as I told you that applications, so we have one of the applications is in warp product. Before